6.5, Temperature and Pressure, Gay-Lussac's Law. In Gay-Lussac's law, the pressure exerted by a gas is directly related to the Kelvin temperature. That's when, let's look at our pistons here. If we keep the volume the same and the amount of moles the same, then when we increase our temperature, then the pressure is going to have to increase because those gases are moving faster and faster and exerting more pressure. And notice it's directly related to our temperature in Kelvin. So when we double the temperature in Kelvin, notice our pressure also doubles. Directly related. So we have our formula, P1 over T1 equals P2 over T2. And so if we know any three of the items, we can solve for the unknown. Well, what if the unknown is the second pressure? Well, we're going to need to rearrange our equation to solve for the second pressure, so you can see how the rearrangement happens. We get P2 equals P1 times T2 over T1. I would suggest writing this down. So, a gas has a pressure of 2 atmospheres at 18 degrees Celsius. What is the new pressure when the temperature is 62 degrees Celsius? So first of all, let's think ahead of time to make sure that we understand what's going to happen. The volume and the amount of moles are constant, so if we're going to increase our temperature from 18 degrees Celsius to 62 degrees Celsius, we're going to increase our temperature, then we know that the pressure is going to directly increase also, directly in relationship to degrees to our Kelvin. So first of all, our answer better be a little bit bigger than 2.0 when we get done. But the other thing we have to make sure is that we convert our 18 degrees Celsius to Kelvin. And the same thing with 62 degrees Celsius. So 18 plus 273 is 291. Second temperature, 62 plus 273 is 335. So when we increase our temperature from 291 K to 335 K, we will have an increase in pressure. So when we plug those values in, 2 atmospheres times 335 K over 291 K, your answer is 2.3 atmospheres, which that is a bigger number, so you know that you have set up the problem correctly. So this time, let's look at this problem. A gas has a pressure of 645 torr at 128 degrees Celsius. What's the temperature in Celsius if the pressure increases to 824 torr, assuming that the amount of moles and the volume remain constant? Well, don't let this trick you. You have to first convert from Celsius to Kelvin. And torr is a pressure. These pressures are the same label, so we can solve this. The only thing is now we're going to solve for second temperature, the T2. So you're going to need to rearrange your formula to solve for T2. You will also need to make sure you convert your degrees Celsius to Kelvin. So 128 degrees Celsius plus 273 is 401 K. And then when we're done, we're going to have to make sure, since it's asking for Celsius when we get done, we're going to need to make sure that once we solve for the second temperature, we're going to subtract 273 to get back to degrees Celsius. So to solve for the second temperature, when you rearrange our law, we have T2 equals T1 times P2 over P1, which is 401 K. Sounds like a money savings plan, times 824 torr over 645 torr is 512 Kelvin. But we have to remember that they asked for it in Celsius, so we need to subtract 273. So 512 Kelvin minus 273 is 239 degrees Celsius, which makes sense because we increase the pressure, and because this law is a direct relationship, that meant that the temperature was also had to be increased. Let's see what this has to do with some real life examples. So vapor pressure is the pressure that accumulates when molecules of a liquid collect over the surface of a liquid in a closed container. In other words, you would kind of think of this is that when you are going to increase the vapor pressure, you're going to increase the number of molecules of a liquid that collect over the surface of that liquid in a closed container. It is very specific for a given temperature, and it increases when the temperature increases. When the vapor pressure of a liquid equals the external pressure, like the atmospheric pressure, the liquid has reached its boiling point. So let's just look at this chart and go down to the last one here just to make sure. So at sea level, we know that water boils at 100 degrees Celsius. You should know that. You might know that it boils at 212 degrees Fahrenheit, which is 100 degrees Celsius, when you're boiling water at sea level. We're a little bit higher altitude here in the Casa Grande area. We're at about 1,100 feet. So our temperature at which water boils is going to be a little bit lower. And you'll notice the vapor pressure of water at sea level at 100 degrees is 760. That 760 millimeters mercury should ring a bell with you. Oh, ding, 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 there's our bell. That is 1 atmosphere is 760 millimeters mercury. And if you remember that, we learned that conversion a few sections back. So if you have a lower temperature, then you're going to have a lower vapor pressure. There's not as much molecules that are going to have gone into the vapor form. We can also apply this to where we're at, how many feet above sea level, which is very important when it comes to cooking, for example. So at higher altitudes, the atmospheric pressure is lower. So because the atmospheric pressure is lower, the boiling point is going to be lower. So in Denver, that's, the mile high, 5,208 feet, the boiling point of water is 95 degrees Celsius rather than 100 degrees Celsius. Therefore, even though you're going to reach the boiling point faster than at sea level, it will take longer to cook if you're boiling something in water. Why? Because if you're boiling something in water in Denver, you're boiling it at a lower temperature. It's like cooking it in the oven. I'm just going to use this analogy. So let's say you have to cook something in the oven and you cook it at 300 degrees. But then you decide that, the next time you cook it, you need to cook it faster, so you put it at 400 degrees. Well, it might burn, but it'll also cook faster the higher temperature. So that was just an analogy. Let's go back to this. If the boiling point of water is 95 degrees Celsius, then it is going to take longer to cook whatever it is you're cooking. So if you're boiling potatoes, we're talking about if you're cooking it in water. So let's say you're boiling potatoes in that water and you're cooking it up in the mountains. It'll take forever to boil those potatoes. Well, not forever, okay, all right, but it'll take a lot longer than normal. I can remember the first time that I did this, and I wasn't really thinking. I was cooking some potatoes and some steak up at Mount Graham, which is very high down there outside of Safford. I was up at a cabin up there, and I said, normally I put the potatoes in at such a time, and then I put the steak in a little bit later. I put the steak on the grill a little bit later, but not much later, because I know normally it's going to take 20 minutes to boil my potatoes. So I planned my steak accordingly. However, that was in Casa Grande. So when I went up to this 8,000 feet cabin, I forgot, silly me, because I was with a bunch of people, so I wasn't thinking. And so I stuck it in when normal. Well, the steak cooked the same amount of time because I was grilling it. However, the potatoes took forever to cook. So we finally gave up and didn't eat the potatoes. We ate the steak. And that was all that we had because the potatoes were still boiling, and because the boiling temperature was much lower because it was a lot lower atmospheric pressure, then it took so long to cook the potatoes in the water. So if you live at a higher altitude, you already know how to do this. I've known of students that when they went from the higher altitude down to the lower altitudes, they had to learn that, oh, it doesn't take as long to when I'm cooking food, boiling food in water down at lower temperatures. So now then, let's think about a radiator, the radiator in your car. It's pressurized. What do you think can happen at the temperature at which water boils when it's under high pressure? Well, it's just the opposite concept. Then you can get the water at a much higher boiling point. Well, let's look here. I had mentioned this earlier. People who live in high altitudes often use pressure cookers. Well, I hadn't mentioned this part of the using pressure cookers. But that's what they do so that it doesn't take forever to cook their food. Well, why do they use pressure cookers? Well, because the pressure cooker is going to increase the pressure, which means if you increase the pressure on the water's heated in a closed container so that pressures above 1 atmosphere are obtained. So you're going to raise the boiling point. So you're going to be able to cook the food faster because the boiling point is higher, because you've increased the pressure much more. So let's see. As pressure increases, boiling point also increases. Think about the purpose of the radiator cap on your car's radiator. The cap creates a pressure cooker situation in the fact that it holds in the pressure so that when you're going to heat up so when the engine heats up, then the water, which helps to cool the engine so you don't overheat, it can reach a higher and higher and higher boiling point so it doesn't boil over. However, if your radiator starts to boil over and you overheat, before you go and spend a whole bunch of money at the repair shop, maybe just go check your cap. The cap on the radiator, maybe it's leaking. If it's leaking, then you're not going to be able to create that tight seal and that increased pressure. So that, the $2 for a radiator cap is worth checking out before you go and spend, $300. Anyway, the purpose of cooking with a pressure cooker. Well, we just mentioned you can cook your food quicker because you are able to increase the amount of pressure, which means you can increase the boiling point. And if you increase the boiling point, that means you're going to be able to cook the food faster. So, which would hurt you more? Or would it be the same? Boiling water from your radiator or boiling water from a pot cooking in Flagstaff? Well, so when that radiator is overheating, they say, don't stick your face over it, when you're going to be taking the cap off. And they even say, be careful, don't do that. But so let's say that you take the cap off your radiator. Well, that water that's in there is much hotter than normal boiling. Why? Because it was pressurized. So you would get hurt really, really, really bad. Whereas, they're in Flagstaff where we have a big elevation and a lot less pressure. Our pot that's cooking, that water is going to have a lot less vapor pressure on it, meaning it's going to be boiling at a lower temperature. So technically, if you had to stick your face in one of those boiling waters, you would definitely choose the pot cooking in Flagstaff. However, that would be really stupid because that's still really hot. But it's not as hot as the heat that is produced in your radiator. So, it's relative of how much burning that would happen. So explain why water boils at a lower temperature in the mountains than at sea level. Press pause and see if you can do that. Atmospheric pressure in the mountains is less than at sea level. The vapor pressure of the water reaches the atmospheric pressure at a lower temperature.